Hey guys, sorry that we got cut off a little short on that video. This was my first video, so we're just trying to make do. Alright, so we already talked about iron 2 nitrate and the fact that it is soluble. The next one is the sodium acetate. So this is the acetate ion. You do need to know that polyatomic ion. So we talked about acetate not having a rule here, but there is a rule for the sodium. Sodium, again, is the group 1 metal. And so what I will see there, I'm sorry, my dogs are barking. But what we will see is that since sodium is a group 1 metal, it will always be soluble. So this compound will also be classified as soluble, and we'll see a little AQ beside it. Just one moment. All right. So our next one is barium sulfate. That's BaSO4. Now we have a rule for sulfates, and sulfates are soluble unless it's with silver, mercury, lead, calcium, strontium, and barium. So barium right here is one of those exceptions. So this compound that you will see would be classified as insoluble. Now remember that insoluble compounds are solids. They form a precipitate when they're made in a reaction. So I have a little demonstration of what these will look like. The first one we have here is the iron 2 nitrate, so FeNO32. Since this is classified as soluble, then I will have the iron and the nitrate wiggling around as little ions in that water solution. They'll be dissociated. Now, why do you think I have 2 nitrates here versus just 1 iron? Well, if you haven't guessed it, the reason why is this is FeNO32 when you crisscross your charges. So since I have 2 nitrates here, that's why I have to have 2 nitrates floating around here as well. The second compound we talked about was the sodium acetate. So sodium acetate, this is one big polyatomic right there. That is also classified as soluble. So you will see it dissociated into its separate ions. And the last one is barium sulfate. We talked about that one being classified as insoluble. So what we'll see here is that a precipitate is formed here, and it is a solid in the solution, and it does not separate into its ions. So these solubility rules are very important for when we talk about net ionic equations, which is on our next slide. All right, so now we have net ionic equations. So we have to be able to take those solubility rules and translate it to this. Now, the purpose of a net ionic equation is to show only the chemical species that are participating in the chemical reaction. So I have an example here to show you. So all that we see here is we have a reaction between aqueous or aqueous, however you want to say it, tomato, sodium chloride and silver nitrate. So this is all that is given to us. So we have sodium chloride, which is NaCl, and we have the little AQ there, and silver nitrate. Silver nitrate is AgNO3 with a little AQ. If you aren't already good at writing these compounds and things like that, then you need to do practice, because we are just shooting out from here. You need to be able to do these. So since they didn't give us the products, we have to first be able to figure out what the products are going to be. So this is a double displacement reaction, and we know that it's double displacement because I have a compound reacting with another compound. If this is the case, then what's going to happen here are the cations, which is the positive charge thing, and the anions, which are the negatively charged things, are going to switch places. So Na is a positive charge, Cl is a minus charge, so we have cation, anion. Ag is a plus charge, NO3 is a polyatomic ion that's a minus charge, so we have cation, anion. So your cations and your anions are just going to switch partners, okay? You always write your cation first and then your anion after that. If you have subscripts here, you do not worry about translating it here. That's the purpose of balancing your equation. So when we crisscross, we have to write like Na, which is a plus charge, NO3, which is a minus charge. So those charges there will crisscross. So I have NaNO3. Then I will have Ag with Cl. You see how they're switching partners. Another way you can look at it is that aldehydes come together and any's come together, just make sure you always write your cation first. So I have Ag, which is a plus charge, Cl, which is a minus charge. So when I crisscross those charges, it's AgCl. Once I do that, I need to kind of classify whether these compounds are aqueous or solids. And I do that by referring to the solubility rules that we just went over. So solubility rules, NaCl is aqueous or soluble because Na is a group 1, and we know that group 1s are always soluble. Silver nitrate here is also aqueous, and we know that because nitrates are always soluble. It doesn't matter what it's paired with. If we look here, we have a nitrate. We also have a sodium, so that is aqueous as well, so that's why the little AQ is here. And then we have AgCl. We talked about this in our example. Silver chloride is one of those exceptions. Silver, mercury, and lead, when it's with chlorine, will form a precipitate, and that's your solid, and that's why it's written here. So this is your chemical equation, but it's not the net ionic equation because the whole purpose is we only want to show the species that's participating in the reaction. So what I have to do is write what we call a total ionic equation, and that shows what is actually happening in the reaction. Like how we were showing on these things, like these are split apart. They're dissociated. So we have to show that in our equation. So if something is aqueous, we write it as its separate ions. And so that's why you see all of these split apart here. This is aqueous, so you write it as its separate ions as well. And then this was a solid. It's classified as insoluble, so that's why we have it stuck together. It hasn't dissociated into its ions. So now we do something that we call getting rid of spectator ions. Again, that is called spectator ions. Those spectator ions are the ones that you see crossed out in red here. What a spectator ion is, think about a baseball game or a football game, right? You have the players which are on the field, and they're doing the action, but then you have the spectators, the fans, just sitting and watching. If we have like a camera and we're trying to televise the event, we're not going to televise all the spectators, all of the fans, because they're not doing anything. They're just sitting there watching it happen. It's important that they are there because they're giving money to the program or whatnot, but they're not participating in the action, okay? So a net ionic equation is kind of like the camera. It's focusing in on what the action is. Now, if your chemical species does not change from an ion to something else, or from something else to an ion, then we call that a spectator ion. It is not changing. It is not in the action of the reaction. So look here. Sodium plus is an ion here. It's also an ion in the product side. So it hasn't changed what it is. So therefore, we would classify that as a spectator. But look at the chlorine. Cl minus here, and then it's in a compound here. Do you see how it's changing from reactants to products? That would not be classified as a spectator ion because that's behaving in the action of the reaction. Same thing for Ag plus here. Ag plus is not a spectator because it is Ag plus in an aqueous solution here, but it remains, it changes to be a solid for silver chloride here. Nitrate is, however, classified as a spectator ion because in the reactant side, you see it as aqueous NO3 minus, and also in the product side, you see it as aqueous NO3 minus as well. So now that we kind of know what our spectators are, we do not include our spectators in our net ionic equation. We only write the reaction according to the action, the stuff that's changing in a chemical reaction. So that's why our net ionic equation is Ag plus Cl minus yields AgCl solid. This is showing the action in the reaction. These other guys are present, they're there, but they're not participating in the equation or in the action. So that is how we write a net ionic equation.